Hi and welcome to this course about feed water measurement with Orifice plates. And the subtitles of this is it possible to extrapolate calibration data from low temperature to higher temperature? And this is a joint work. My name is Peter Claesson and my colleague is Peter Lau and Oliver Bücker. And this research has been done within the project Metrology for Improved Power Plant Efficiency. It's a research project funded from the European Union within the EMRP-programme. The background is feed water flows measurement in power plants, and in a power plant you can have like 1000 megawatt, and then you have a flow rate of 1800 kilos per second, and temperature is up to 250 degrees. You can have pressures about 80 bars, so it's really high temperature, high flow rate, and how high pressure. And you have several influences factors of the measurement uncertainty. You can have the disturbance, flow profile, calibration, and the time from the calibration drift of the sensor. And if you're going to reduce the influence of the disturbances, you only do that with on-site calibration. But on-site calibration is very complicated and expensive. But for Orifice plates that is normally used in power plants, you have some guidelines due to experiments of how large the uncertainty can be. And as mentioned, the most commonly used techniques in power plants is differential pressure flow meters. You measure the differential pressure of some kind of construction. It can be an orifice, a venturi, or a nozzle. And yeah, by the name of it, you actually measure the flow rate indirectly, since you measure the pressure and not actually flow rate. And you have all kinds of standards that providing restrictions of how the design of this flow meter should look like. And if you follow those standards, you normally get an uncertainty of 0.7 to 2% under perfect conditions. And the standard I talked about is this ESA standard and the ESMA standard, and they're based on several years of experiments from different laboratories. And the basics is for the Orifice plate was done of Bernoulli, so it's the Bernoulli equation, and the flow rate is given here. The flow rate is equal to this discharge coefficient, and then you have a square root 1 minus a beta, and the beta is the difference. You take the smaller diameter of the orifice divided by the pipe diameter, and then you have some other factors. You have the differential pressure comes in here, and you have the density, and you have the small contraction diameter again. The Reynolds numbers is numbers that normally is used when you describe flow conditions, and Reynolds numbers really depends on the pipe diameter and the flow rate and the viscosity. And this discharge coefficient that's a really important factor for this beta is just the geometrical factors, the pressure you measure, the density, and this epsilon is water properties. Here is the diameter of the construction again, so this discharge coefficient, that's a dimensionless constant that you need to determine to be able to calculate the flow rate when you use a Orifice plate. And the really question is, how do you actually determine the discharge coefficients? And the best way to do it is to do a calibration. But if that's not possible, as we talked about earlier, that it can be very complicated and expensive, you have those two standards that describes a way of how to calculate it. And if you have a venturi tube, the discharge coefficient is around 1, roughly 1, and you have an uncertainty between 0.7 and 1.5%. For an Orifice plate, you normally can determine the discharge coefficients with an uncertainty as low as 0.5. And in those standards you use this Reed-Harris-Gallagher equation. And this equation is a quite large equation, as you see here. The discharge coefficient is equals to this long expression that depends on the Reynolds numbers and this beta, and to remember, the beta is the small diameter divided by the pipe diameter. And then there's some other factors. You have like M2 and you have L1 here, and L1 is the spacing between the upstream pressure tapping divided by the pipe diameter, and a smaller L2 that comes into the factor M2 is the spacing to the downstream pressure tapping divided by the pipe diameter. And this M2 you see it here is this L2 and divide by 1 minus beta, and beta is this one. And then you have this factor A as well that depends on the Reynolds number and this diameter quote, this ratio, the diameter ratio. So it's a kind of complicated expression. So, but if you have the Reynolds numbers, all the rest is just geometrical factors. You have the ratio by the diameters, and this is the spacing between the upstream and downstream pressure tappings comes into the rest ones. And that's just geometrical factors, and then it's just some constants and calculate. But the difficult thing is to know Reynolds numbers, and as we talked about earlier figure here, the Reynolds numbers really depends on the flow rate. So be able to calculate the discharge coefficient that you need to calculate the flow rate, you need to know the flow rate to start with. So it's it's a really tricky situation. Yeah, and here we have it. You have the flow rate and you have the discharge coefficient. So you need to know the flow rate to be able to calculate the discharge coefficient, and you need to have the discharge coefficients to calculate the flow rate. And in addition to this, you have a lot of parameters like the diameters and the viscosity and the density. They depend on the pressure and the temperature as well. So you really have a hard problem. Here you have the discharge coefficient depends on the Reynolds numbers, and Reynolds numbers depends on the flow rate, just in equation. So it's a really tricky situation on how to do it. So the solution that people are doing is, of course, the best thing was to do some kind of iteration, that you guess some kind of flow rate and calculate the Reynolds numbers, and then go back and forth, or I actually do a calibration. But yeah, it is really hard to do calibration at the working conditions in the power plant. So you don't have any calibration facilities that actually can do that. So what you do, what they have done is you establish a relation between the measured pressure and the nominal pressure. So you have this, you measure the pressure and divide it by some nominal pressure, and to this nominal pressure you have a flow rate, and then you can calculate the actual flow rate. And this is valid as long as the actual flow rate is deviating too much from the nominal flow rate. The largest uncertainty is actually what kind of discharge coefficients you're going to use for this nominal flow rate and pressure. So the real ideal would be to do a calibration under working conditions and use different flow rates, temperature, and pressures, but you have no facility available that can reach those temperature and flow rates and pressures. And that's the whole idea behind this research project, that we want to find some kind of model that you actually can do a calibration at normal ambient conditions, and then have an extrapolation model that can extrapolate up to the working conditions. So what we've done a lot of measurements with Orifice plates, and our colleagues have also done it on other flow meters, ultrasonic flow meters and Venturi tubes and electromagnetic flow meters, and the result of that can be found on the project homepage. But with this one, for the Orifice plate, we did a lot of measurements. We changed the Reynolds numbers up to 1.2 million, and we changed the temperature, used a lot of different temperature between 20 and 85 degrees. So all those dots is the measured values. The red one is our extrapolation model fitted to all of these. And the green one is the Reader-Harris-Gallagher equation. So we can compare our discharge coefficient with the standard given in the standard in the ISO 5167, and according to this standard you can have an uncertainty of 0.5%, and in most part our measured values is actually within this limit. So the Orifice plate is really fulfilling the requirement in the standard. So that's nice. And the nice thing is our model is really have the same shape as the Reed-Harris-Gallagher equation. And if we looked at the measurement data and take the deviation between the measurement data and the theoretical Reed-Harris equation, we end up at this plotted as a function of Reynolds numbers, and here we have the different temperatures. So we see that for at least like 200,000 we are within this limit 0.5%, and it seems like the deviation approaches constant offset of maybe 0.35%, minus 0.35%. So that's really cool. So the comments and a really conclusion we did that our office plate describes, or the Reed-Gallagher equation describes the office plate quite well, and our office plate is in agreement with the standard. And the good thing is that the charge coefficient is actually follows the Reynolds numbers. So then we propose the extrapolation model that's much simplifies with the Reed-Gallagher equation that only depends on the Reynolds numbers. So you have three constants, M0, M1, and M2, and then you have the Reynolds numbers. And this means that you can actually calibrate the orifice plate at ambient conditions and determine those constants. And then you can just extrapolate up to the working conditions where you more or less know the Reynolds numbers, and then you can calculate what discharge coefficient you should have. So here is an extrapolation where you actually extrapolate. We did a fitting to our data and got those fitting constants, and then when we extrapolate we actually end up here, so we can extrapolate up to 250 degrees or up to 300 degrees if you like, and can get a value of the discharge coefficients. So how we actually do this is we have a little sketch of how to actually do the calibration. So you determine those constants at the calibration, and you put them in. You have a drift and pressure from the actual working conditions, and then you can determine and calculate the density, viscosity, and the two different diameters, the actual size of them at the actual working condition. And then you guess the flow rate and you calculate the Reynolds numbers from the Reynolds numbers equation. You put the Reynolds numbers in the discharge coefficient, and then you use that discharge coefficients to calculate the flow rate. And then you iterate this until you get the stable value of the discharge coefficient. So we did that. We had the actual flow rate was around, we actually did a guess in this middle column that we have a flow rate about 23 kilos per second. So I calculated the Reynolds numbers, and in this first step we actually did a first intelligent guess of the discharge coefficients, and in this column we didn't do any guess of the discharge coefficients. And what you actually see here, if you make no guess at all, in only 3 iterations you get a really stable value of this discharge coefficient. And here when you made an intelligent guess between the second and third step, you have the same value. So it really converts very fast. So in summary, we've done some research about how to find an extrapolation model that you can calibrate the orifice plate in ambient conditions and extrapolate up to higher temperature. We propose a very simple model that only depends on the Reynolds numbers, and for our orifice plate it seems to work quite fine. To really determine if you can use this model, you should need to do some measurements up to if you can find a facility that be able to generate temperature up to like 150 degrees, and then you can actually validate if this discharge coefficient is around here, and validate the uncertainty of this model. So that is the next step, but so far we have proposed a very simplified model to calculate the discharge coefficient on the Reynolds numbers. Yeah, so that's it. Thank you for your attention. I wish you a pleasant day.